Okay, so for chapter 5, remember this is area of a sector, it says. So you really can think of a sector almost like a triangle, I said. And this is kind of like the base and the height. And this base is the arc length, so this is r theta. And this height is the radius of the circle. So you really could kind of cheat and get away with writing down the area of a triangle here. 1/2 times base times height. And this gives you area equals, go away, 1/2 r squared theta, which is the formula I gave you in the notes. But it's a nice, easy way to kind of rederive it if you forget it. Just think of it as a little triangle. Now, it's not a triangle, so the reason this works is a little bit mysterious. It has to do with the fact that we're working in radians. Okay? And so that actually worked out real nicely for us. But anyway, you now have the radius, you have a formula, you have the theta. Okay, so area is just basically 1/2 times 7 squared times pi over 4. 49 pi over 8. I'll write my answer at the top. 49/8 times pi. The same thing with the second problem. You have a formula for this. This is the arc length, r theta, s equals r theta. But you really need, you can't use 18 times 240. You need to use 18 times the radiant equivalent of 240. If you remember from your unit circle, that's just 4 pi over 3. So you need to multiply by 4 pi over 3. Don't use 240, or you'll find that this arc length is like 2,000 inches, which is impossible. Okay? So it's 24 pi inches. So some of you guys multiplied 18 and 240. That's a big number. I don't think that's how long that little piece of blue is. Okay? The next one is just converting DMS into decimal degrees. So degrees, minutes, seconds. And then I didn't actually have you enter this because you didn't have a calculator. I just had you write this. But if you did enter it, it comes out to 36.42 degrees. Technically 4205 repeating. So I'll just write the whole thing. 36.4205 bar degrees. Okay, next is this one, 14.11. So you already know that this is 14 degrees and so many minutes and so many seconds. And if 0.11 is 0.11 hundredths, or 11 hundredths, I mean, then you could think of that as how many 60ths is that? So you can just basically take 0.11 and multiply by 60, which gives you 6.6. That tells you that there are 6 minutes and some extra seconds left over. Then you can take the extra 0.6 and multiply by 60 again, and you get 36. And that gives you the seconds. There you go. Okay, but those are kind of all calculator problems, like numbers 3 and 4. So I doubt it will be on the final, because I don't think I would test you on something with a calculator and then say don't use a calculator. So let's go on to next problem. Coterminal means same terminal ray or same position on the unit circle. So you have two options. You can either add 2 pi and subtract 2 pi. That's one way of going around the circle. Or you convert to degrees and use 360s. Okay, so if you add 2 pi, you're going to be doing 11 pi over 30 plus 60 pi over 30. That's like adding 2 pi, which gives you 71 pi over 30. If you go with the subtraction, you're doing 11 pi over 30 minus 60 pi over 30, which gives you negative 49 pi over 30. And this is all very awkward in radians. If you think of this problem in degrees, it's actually quite simple to understand. If you take this and multiply by 180 over pi, you realize that this is just 66 degrees. And if you add 360 to that, you get 426. And if you subtract 360 from it, you get negative 294, which is the exact same thing as above. Okay, 15 pi over 4. You can think of pi over 4 as 45 degrees, right? Because you've been working with pi over 4 quite a bit. So just think of it as 15 times 45 degrees. Okay, now I know you don't have a calculator, but just bear with me. Let's rotate 45 degrees 15 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It looks like we're over here at 315 degrees. In other words, it looks like we're in quadrant 4. So I just basically, each of these little bubbles represents 45 degrees. I just did 15 of them, going all the way around. Okay, negative 200 means you're going backwards 200 degrees. So this is 90, 180, and a hair. So it looks like a good drawing might be something like that. So make sure you always go counterclockwise with the negative angle. Okay, let's go on to this page. State the quadrant that the terminal side of each angle lies in. So again, you can think of pi as 180, that's really what it is in degrees world. So if you want to think of it as 180, that might help you. You think of it as negative 11 ninths of 180. And this just reduces to 20. So this is just basically negative 220 degrees. So I like thinking in terms of degrees when I'm graphing. Negative 220 degrees would be sort of where number 7's answer was. So right about here, I'd say that's quadrant 2. Okay. Quadrant 2. Let's go to the next problem. These are very, very important to me. Okay? If you haven't noticed, I kind of care about domains and transformations. If you haven't picked up on that by now, I could probably put it in my classroom management plan. I actually put something in my classroom management plan like Mr. Shore teaches lots of domain range and stuff like that. So anyway, it's a lot of graphical, but this is a complicated problem. And is it the same one you had originally? Because I think I changed these a little bit after I gave you the exam. Okay, so let's do the problem, of course, that you have, right? So I'll cross this out. So what is the problem that you have? 1/2 secant 1 theta over 2. Okay, yeah, thank you. I had to update this test. So actually, it's this problem, isn't it? Interesting. Okay, well, anyway. So this was your number 9? Yeah. All right. So you have to know what the numbers mean, right? And you might want to write this as 1/2 secant of 1/2 x. See? Okay, so what do the halves mean? Well, the first half on the outside means vertical compression. And this half on the inside you'd think means horizontal compression, but it means horizontal stretch. Remember we said it's counterintuitive. Okay, so we have to perform a horizontal stretch and a vertical compression at the same time, or we just do it in phases. Okay, so remember, secant, I'll just do a couple rough sketches here. Here's cos, oops, that's sine. Here's cos. All right, that's cosine. Here's secant. So I'm just kind of getting a secant graph going so I can remember what it looks like. Okay, so that black thing is secant x. And now, I'm going to identify real quick. This asymptote is at pi over 2. I think I remember that. This is at negative pi over 2. Okay, now I can transform it because I know what it is. So I'm going to be doing a vertical compression. So what's going to happen is this is just going to be at 1/2 instead of 1. Like normally that's at 1. Now that's a half. Okay, and then also I need to do a horizontal stretch. So I'm just going to double my asymptotes. Okay, so if I multiply these by 2, what's negative pi over 2 times 2? Negative pi, right? Okay, so I think I'm figuring this out. I think I've got an asymptote at negative pi and another one at positive pi. I'm finally ready to kind of sketch. And then I've got this weird parabola-looking thing in the middle, like this, that passes through 1/2 on the y-axis. And then I'll see another piece over here. Like that. Another piece maybe over here. So by spacing out my asymptotes more, I did my horizontal stretch. By putting my y-intercept at 1/2 instead of 1, I did my vertical compression. Normally this would be at 1. So I got both halves that's really hard to learn, partly because the graph itself is hard to memorize. How many of you, when you can't remember what secant looks like, you draw yourself a little cosine wave, and then draw the u's and the upside down u's coming off the peaks and valleys? Anyone ever do that? That's a great way to memorize the cosine graph. I'm sorry, the secant graph. Make sure you have cosine and sine memorized, and then just put these on here. Notice that whenever cosine is 0, see, whenever this thing hits the x-axis, secant's going to be undefined because it's 1 over 0, and that's why you get an asymptote right there. So all the roots of cosine represent vertical asymptotes for secant. Okay, now let's go to the next one. What was your next question? Number 10.
No, I think it was -3 sine, in parentheses 2x minus pi.
Okay, it says 2x minus pi, like that, right? And then plus what?
1.
Plus 1. Okay, there's a lot going on in this problem. So I would suggest you actually pull the 2 out. Obviously you can't pull it all the way out of the sign, but you can pull the 2 out like this. Does anyone remember why we want to probably do that? Why is that important?
So you can see where you're shifting left.
Yeah, it's clear now that there's a right shift pi over 2, right? That was not so obvious a minute ago, but it's very obvious now. Okay, so all the numbers mean something, right? And it's a sine wave. Okay? So there's so many ways to do this. You can try sketching a sine wave and then messing with it. Or you could write down some values of sine that you know. For example, you probably know that sine of 0 is 0. You probably know that sine of pi over 2 is 1. You probably know that sine of pi is 0, and so forth. See what I'm saying? So you could kind of write stuff like that down and transform the numbers. Or you could sketch sine like this and play around with it. Okay? So we're going to follow dilation, reflection, and then translation. So the first thing is I have a 3 right there. That's a vertical stretch. So we have a sine wave that can reach all the way up to 3 and all the way down to -3. That's my first clue. That's because of the 3. It's also upside down because, oh sorry, I need to do one more dilation, sorry. Right here, this 2. 2 means it's wider or narrower. Narrower. So normally this little S shape that I drew ends at 2 pi, but it's going to end at pi, see? That's my next clue. So I just figured out what the 3 and the 2 means. The 3 extends it upwards and downwards. The 2 compresses it. Instead of ending at pi, ending at 2 pi, it'll end at pi. How do I know? Because it's been compressed. Okay, now I can perform my shifts. Oh, first I got to reflect it upside down. Then I'll perform my shifts. So I'll flip it upside down. That's easy. That takes care of that. So all I'm left with now is basically right shifting by pi over 2 and upshifting 1. All right. So this point is at the origin, point A, right? But I'm planning to right shift by pi over 2 and upshift 1. So that point A is going to end up right here. From here, the amplitude is 3. And this is all going to end. This is at the point pi 0, this point B. That point is going to go over pi over 2 and up 1. So it's going to end up at 3 pi over 2, up 1. And you can see this is quite narrow. My graph's going to have to look like this. I don't know if your graph paper is scaled the same way as mine. It actually needs to go even higher than that. It's supposed to extend 3 above and below these points. So it goes down 3 spaces, back up to here, and then up 3 spaces and back down to here. So all this happens very quickly. Yeah? I know. It is a little different. I don't know what your scale is on there, but basically you need this thing and then shift it to the right, pi over 2 and up 1. So wherever your graph paper is. Okay. And you don't want it to be too wide because, look, from here to here is only supposed to be pi, which is only a wide. It's only ½ inch, you know, on my paper here, so I had to keep it real skinny looking. Maybe your paper looks a little different. The most important thing to know is what the numbers mean and what the parent function looks like. And then you can move anything. Okay, here's a tan graph. I think this is the exact same problem that you guys had, right? So I don't need to modify that one. All right, so what does this half mean here? Vertical shrink. And what does this, so this is a V shrink, or vertical compression, you could say. And 2x, what's that?
Horizontal compression.
Horizontal shrink or horizontal compression, right. Okay, so I need a tan graph. Tan looks like this. But I need to horizontally compress it. So what's going to happen is my two asymptotes are not going to be at negative pi over 2 and pi over 2. They're going to be at negative pi over 4. Pi over 4, you're dividing by 2. Okay, so you're going to have an asymptote right there. Let me do that in red so you can see it. So you have an asymptote at pi over 4. There's actually another one at negative pi over 4. Okay? And I don't know if you remember this, but the tan graph contains the point pi over 4 comma 1. In other words, tangent of pi over 4 is 1. So that point just got squished to pi over 8 comma 1, see, when we did that. So this is the curve. Now I haven't done the vertical compression yet, okay? I just did the horizontal compression, bringing the asymptotes closer to the y-axis and this point as well. So it's at half of pi over 4. And now I need to do a vertical compression. So that point that's at pi over 8 comma 1 is now going to be at half. So in blue, here's my final answer. It has to fit between the red asymptotes, and it has to look like it's been vertically compressed. So the better your graph paper, the better this will look, of course. But I'll draw a rough sketch of it over here. Maybe that's even better. These are now at negative pi over 8. I'm sorry, negative pi over 4. Positive pi over 4 because of the vertical compression. Okay? And then there's the curves in here, of course. And this point, if you must know where it is, it's halfway between the y-axis and the asymptote. That's at pi over 8 comma 1 half. Used to be at pi over 4 comma 1, but we've had a double compression. So that says pi over 8 comma 1 half. And of course it's an odd function, so you have negative pi over 8, negative 1 half as well. And there are many other points. Let's go to number 12. Number 12 says, state which trig functions are positive for the angle negative 5 pi over 6. And I felt a little bad for you guys if you missed number 7. I think it was like some of this early stuff, right? Like if you go back to like number 7, right? Number 8, if you didn't know what that negative meant, you missed a lot of points on this test. You know what I mean? You kind of got triple jeopardized. But this happens again. See, you've got a negative angle, and you can just think of that as 180. What is negative 5/6 of 180? Well, that's just negative 150, see? So if you sketch it carefully, you realize you're actually in quadrant 3. And all students take calculus will tell you which trig functions are positive. So it's tangent that's positive, because we're in quadrant 3. And of course, the reciprocal of tangent would be positive, because anytime you flip a positive number upside down, it's still positive. So the answer is tangent and cotangent. Okay? So for full credit, you needed both. I did say which trig functions, plural. Let's go to this next one. Find the speed of an object in inches per second if it's making 3 revs per minute on a circular path radius 10 at a constant velocity. Leave your answer in terms of pi and include units. So I know that this is kind of a stretch for some of you, but we're trying to incorporate some of the things we've learned in other classes too. So you're going to just try to take 3 revs per minute and convert it to inches per second. That's what we're trying to do. So let's just write 3 revs, 1 minute. And ultimately, we're trying to get a certain number of inches per second. That's our goal. So we can just use dimensional analysis to solve this whole problem. So the first thing is multiplying by a statement that would remove minutes. How about 1 minute is 60 seconds? That gets rid of minutes and introduces seconds. So I've accomplished my time unit. Next, I need to get rid of revolutions and replace them with inches. Well, we're talking about a circle with radius 10, a circle with area 100 pi. It's a circle with circumference 20 pi. You know, this is the big clue. The circumference of this circle is 20 pi. So 1 revolution is literally 20 pi inches. So that's how I plan to get rid of revolutions, recognizing that that's just a circumference. Now it's just basically 60 pi over 60. Okay? Okay, negative 495. If you don't like this angle, you can add 360 to it. Nothing wrong with that. It's not going to change anything. If you still don't like it, add 360 again. There, you like that question better? Cosecant 225. Go over here and find 225 on your unit circle. If you're looking for cosecant, you're going to have to flip that sign upside down. So what is 1 over negative root 2 over 2? Turns out it's just negative root 2. Next one is a little more straightforward. Secant 120. Remember, cosine of 120 is negative half. So secant would just be negative 2. Negative 2 over 1. It's just the reciprocal of your cosine. So notice, I don't even care what the like coordinate is. On the unit circle, cosine of 120 is negative half. Therefore, secant must be negative 2. Okay, next is cosine 660. I really don't like that angle. I don't like it. I'm just going to take away 360. So let me ask the question again. What is cosine 300? Oh, okay, that sounds more familiar, see? Cosine 300 is a half. Cosine 300 is a half. Okay, just straight off the unit circle. 585, yuck. Now, cotangent has a period of 180. So you could actually subtract it 180s if you wish. Keep taking away 180s. You could do that with tans and cotans only, okay? Just start subtracting 180s as much as you want. If you do it 3 times, it brings it down to the simple problem, what's cotan 45? The answer is 1. So I realize that 585 isn't technically one of the unit circle special angles until you look at the coterminal version, 45. But 585 is the same thing as, well, 585 is not even coterminal with 45, but they have the same cotan. Because cotan repeats every 180, so you can just subtract 180 as much as you want. Or you can just subtract it twice, and you'll be doing this problem instead. If you only subtract it twice, you get cotan of 225, which is also 1. So it doesn't matter. Maybe you like that better. Subtract 360, which leads you to this problem. Okay, so understanding coterminality and periods. All right, let's go down to number 18. Okay, so this is a cosine graph. The amplitude is the absolute value of that number. So the amplitude is 4. The period is supposed to be 2 pi over omega. Omega is right there. So it's 2 pi over 8. The phase shift is negative phi over omega. This is phi. So it's negative pi over 6 over 8. So it's pi over 48. And the vertical shift is just chilling right outside. That's the negative 4. Or you could say down 4 is a nice way to say it. Now, is this just a bunch of new material? Not at all. Vertical shift, Amplitude is the same thing as vertical stretch. Okay? Period is the same thing as horizontal compression, or horizontal shift, horizontal stretch. Phase shift is the same thing as horizontal shift. So watch what happens if you just rewrite this problem. If you pull the 8 out real quick from the inside, and we'll use x instead of theta. If you pull that 8 out, you understand that this graph is a vertically stretched, horizontally compressed, right shifted, downshifted cosine. Right? So the vertical stretch is your amplitude. 2 pi used to be how wide it was, and now it's down to 2 pi over 8. That's your period. See? Then the right shift is pi over 48. You can see it right here. It's also known as phase shift. What happened was the scientists got to this, and they wanted names for everything. Normally we just call it horizontal shift, but they're like, oh, we're going to call it phase shift. So, phase shift for that. And then, I guess the scientists and mathematicians both agree that's the vertical shift. Okay? We do the same thing with this problem. Now, there's no amplitude on a cotan wave, because it's not really a wave, you know, it's like more of a repeating pattern. Cotan looks like this. So we wouldn't call it like amplitude, because amplitude means like highest and lowest points. So you would just put none. There's no amplitude. For the rest of it, you can just factor it out. So pull that 5 out real quick, and you can see it's x minus pi over 10. Okay, so when it comes to the question of what is the period, understand that normally in the fundamental period, like on the regular parent function, everything kind of starts and stops between 0 and pi. So that's the whole graph right there. Everything else is just a duplicate of that. So the period is 0 to pi, just pi. It's not 2 pi anymore. So you would just divide by 5. That's your horizontal compression. And then you would do a right shift to understand the phase shift. So it's pi over 10 to the right. Looks like Mr. Shore is being a little sneaky. He put his vertical shift in the front, but it's still up 4. Whether you put 4 plus 9 cot or you put 9 cot plus 4, it doesn't matter. It's still a plus 4 there. Let's go to the next one. This is a cosecant graph, which looks like this. With lots of transformations, of course. But I wouldn't say there's an amplitude. There's just a vertical compression, but you don't call it amplitude. Okay, so think of this as, if you pull out the 1/5, you can think of this as x minus 25 pi over 6 minus 2. Looks like my period used to be 2 pi, but I'm dividing by 1/5, see? I'm stretching it to 10 pi. And that agrees with our idea that a fraction on the inside, a 1/5 on the inside means a horizontal stretch. So 10 pi is the new width of each cycle. And there's definitely a right shift of 25 pi over 6. And there's a downshift of 2. There you have it. Okay, this next problem doesn't have to be really hard, okay? If you understand that your answer is going to look like this. Y equals a number times sine of a number times t minus a number plus a number. In other words, all these graphs we've been doing with the shifting and stretching and all that garbage can be applied to a moving object that repeats its pattern. Okay? So whether it's an object going around a circle like this, or swinging back and forth on a wire, or sliding back and forth on a wire, you can use sines and cosines to find where they'll be at a given time. Okay, so our goal is to create a little function where if you tell me what time it is, I can tell you exactly where it is. A formula that's able to predict the future. Like I could plug in 1 year and know exactly where the object is. Even if I choose to go to Hawaii for a year, I can come back and there it is, right where I expected. Okay? So that we call a model of its position function. Now technically it's an object moving back and forth on the x-axis predictably. Like this. Just back and forth. And so the time is the independent variable. x is changing as a result of this. So this would technically be an x. I know it's weird to change y to x, but in this problem, the independent variable is time, and the dependent variable is technically x. Okay? I don't care about y. The y is always 0. The object is on the x-axis going back and forth. Y is always 0. I want to know what the x is at certain times. Okay? So that's the idea. That's what's going on. Most of this stuff just has a formula. So what I'm going to do is just draw a quick picture. The object's moving between two fixed values on the x-axis. Okay? And if you read it carefully, it says that the leftmost position is -3 when the time is 2. And the rightmost position is x equals 5 when the time is 6. Okay? Nothing ever happens outside of this. The object is literally moving from here to here and back again, and this just goes on forever. Back and forth, back and forth, back and forth. Okay? All right. So the first thing I might want to do is understand that the amplitude is actually 4. Why is that? If you draw a line in the middle, where x is 1, that's halfway between -3 and 5, okay? The distance on this side is 4 inches, or whatever, 4 miles, 4 inches. And then this is 4 inches, see? So the motion is 8 units wide, from -3 all the way up to 5, but amplitude is defined as half of that motion. So it's 4 here and here, and x equals 1 right in the middle, see? Or you can just use a formula real quick to get the amplitude. I actually gave you a formula for it. The amplitude is the largest x minus the smallest x all over 2. So you could have just gotten it that way, but you might not understand it. So you're just trying to find how wide this thing is and then divide it in half. Okay, the period is something you just have to think about. Okay, so the period is always 2 pi over omega, right? And sometimes you know the omega and sometimes you know the period. Period just is how long it takes to repeat itself. So if it starts at t equals 2 and makes it to the right by the time time is 6, how long did it take to go from the far left to the far right? It went from time equals 2 to time equals 6. How many seconds is that? 4 seconds to go across. And then it's got to come back again. So how many total seconds for one cycle? 8. Okay, so this is going to be, omega will be 2 pi over period. Period is clearly 8 seconds. So it looks like my omega is pi over 4. So I'm starting to get clues here. I think my A is 4, see? My omega is pi over 8. Pi over 4. These are big clues. And they're kind of formulaic. You could do the same thing every time. What does B mean? So it's the vertical shift, right? But we're used to seeing graphs like this, you know, where this is x and this is y, and the vertical shift is sort of the middle range value. See? So B is the middle range value. Well, domain is time here. Range is x. So we're talking about that middle x value, that 1 right there. That's what goes here. And I gave you a formula for that too. B is just largest x value plus smallest x value over 2. So you can just average the extreme positions. This leaves us with one last question. What is phi? Okay? And for that, there's no formula. To get the model complete, you need to start with the fact that x is equal to 4 sine pi over 4 t minus phi plus 1. And you need to plug in one data point. You can use this set of data or this set of data. It's up to you. But you're going to make x -3 and you're going to make t 2 and you're going to solve it. So you're going to make this -3 and you're going to make t 2, so this is going to be a pi over 2 now. and you're going to solve it, and you're going to find out that pi is actually the value of phi here. And at that point, you'll have your full model. Okay, so I'll stop this one. But I think phi came out to pi. Does that sound right? I'm pretty sure. All right, so that's tricky. Okay, nothing easy about it, but it is a little bit predictable. And then this problem really threw people for a loop. Here's a circle, and we're going to travel along the circle 3 diameters. Okay, so that's kind of weird. We're going to start here maybe. 1 diameter is about yay long. I'm going to wrap that onto the circle 3 times. So I'm going to go 1, 2, 3. Weird. How many radians is that? Yeah, it's 3 radians. Why? Because this is 6 radii, right? To travel, in order to travel, I'm sorry, this is 3 radii. 3 radii is equivalent to 1.5 diameters. Isn't that true? So remember this formula, S equals R theta? I have just traveled 1.5 diameters. 1.5 diameters. So I didn't draw my picture quite right, sorry. I was going to go 1.5 diameters. So here's 1 diameter, and here's half a diameter. But that's technically 3 full radii, okay? Radius, 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 R, R, R. So I can just replace this with 3R. That's the traveling distance. And the angle is 3. Okay? The next one, this next statement is actually true. And the reason it's true is, remember, tangent is an odd function. Can someone remind us what that means? Origin symmetry, right? Also, f of negative x is the same thing as negative f of x. In other words, I could pull a minus sign out of here. Watch. First, I'm going to write the inside as the opposite of x minus pi over 2. That's exactly the same thing as 2 over pi minus x. Pi over 2 minus x. Then I'm going to pop this negative out because it's an odd function. I have every right to do that. See, the reason I do this is I now totally get this. I know exactly how to draw it. I'm going to take a tan graph, flip it upside down, and shift it to the right. So here's a tan graph. I'm going to flip it over, slide it over, and the graph looks like this. And that, my friends, is a cotan graph. Exactly. So this is true. So what's really important to learn is when you can move the negatives around. I didn't like how it was written like this. I couldn't tell what the shift was. I wished it was the other way. So I put in a negative, I factored out a negative, making it the way I wanted it to look. And then I know it's not a function, so I can pop the negative all the way out. And this just means an upside down right shifted tan graph, which is a cotan. Let's try the same idea with that one, except it's actually a little bit easier. This is just a right-shifted cosec graph, is all it is. So a right-shifted cosec graph would, if this is cosec, this is cosecant. If I right-shifted this thing, it would look like this. Pi over 2 is not a big shift. But I don't think that's a secant graph. That red graph doesn't look like a secant to me. It looks kind of upside down. If it was a secant graph, it would look like this, with this piece on the y-axis. That's secant. So the red, it doesn't quite match. It's upside down, so this is false. Now, if there's a negative, if it was cosecant of x minus pi over 2 equals negative secant, it would actually be a true statement. But you know I need at least one true and one false here, right? All right, almost done, I think, right? Isn't there one more page? How much more we got? One more page, and there's a bonus page. Okay, so I scrambled these because I didn't want you to think that we always do sine, cosine, and tan, and then, cosecant, secant, and cotan, always in the same order. And I need you to know the definitions. So it'd be nice to just kind of go through here and write these down. This is y over r and x over r, and y over x, and then the reciprocals are, oh, see, I already fell for it. It's y over r, x over r over x, x over y, r over y, and x, y over x for the last one. Okay, so let's get that nailed down first. We don't have to think about it. Looks like we're going to need to know r, so negative 6 is my x, 9 is my y, figure not drawn to scale. I think I need that radius. Okay, so the radius is going to be the square root of 81 plus 36, which is the square root of 117. Awkward. Okay, but that's r, and so I can just run through here now. 9 over root 117. Negative 6 over root 117. Negative root 117 over 6. Negative 6 over 9. Root 117 over 9. And 9 over negative 6. Some of this stuff simplifies. You might want to get rid of the radicals in the bottom. Some of these fractions reduce, like 6/9 is 2/3 and 9/6 is 3/2. Well, let's move on. Okay, find the domain and range of the function. So this is a sine wave. It has been vertically stretched. Oops, it's a cosine. It has been vertically stretched so that its amplitude is 2. So I think the range is going to be pretty easy to figure out. The range is basically negative 2 to positive 2. Most people got that right. Domain, this thing just goes on forever in both directions, so it's just all real numbers for domain. So what about this vertical, what about this horizontal compression here? There's a 2 pi on that x. What about the left shift that's involved? Well, those are important, but they don't affect the domain. If you have a graph that's infinitely wide, and then you vertically compress it, it's still infinitely wide. I'm sorry, horizontally compressed. If you shift it over, it's still infinitely wide, see? So that doesn't change the domain. Let's go to 27. So for 27, we have a tan graph. So this is the parent function for tan. And notice it's infinitely tall, right? It goes infinitely upwards, infinitely downwards. So no matter what you do to the range, you're not going to change that. This range is all real numbers, no matter what we do. But the domain is tricky on this one. So you first have to know the domain of a tan graph. Okay? You have to know what the domain of a tan graph is. So remember, the forbidden angles on a tan graph are at pi over 2, 3 pi over 2, 5 pi over 2, negative 1 pi over 2, 99 pi over 2, negative 99 pi over 2. In other words, x cannot be an odd pi over 2. Most of you have this memorized, it's on your flashcard, and some of you wrote it for a final answer. But this is true for an unmessed with tan graph. Okay? Now, if you're planning to mess with the tan graph and stretch it and squish it and slide it, that will change. But you can still start with this basic fact. Okay? So let's talk about the changes that have occurred to the x's here. There's a 4 there, and there's a pi over 2 there. Let's pull out the 4, first of all, so that we can see clearly what's going on. If you pop that 4 out, you get, hold on, eraser's getting in my way there. There we go. If you pull that 4 out, you can see very clearly what's going on with the x's. There is a horizontal compression, factor 4, and a left shift by pi over 8. So watch what I'm going to do. Here's my answer. Ready? I'm going to divide by 4, because all the asymptotes are going to get treated that way. All x's are, even the forbidden ones. And a left shift of pi over 8. Done. Now this can be cleaned up, but I accepted this answer. So what did I do? I wrote down the rule for domain, then I applied the horizontal transformations, which will affect that domain. Okay, you play the same game here. Let's draw a quick cosecant graph. That's cosecant, just the basic. And you remember that there's an asymptote at pi, there's an asymptote at 0, there's an asymptote at 2 pi. So in other words, k pi is forbidden. But that's before messing with the graph. Let's see what kinds of things have been done to this graph. If you pull out the 2 pi, you can clearly see what kinds of changes have taken place. First of all, there's a horizontal compression of 2 pi. So you'll divide by 2 pi. And there's a left shift of 1, so you'll take away 1. That's the answer. So I took the old domain rule and divided by 2 pi and took away 1, because that's what's going on. That's what changes have been made to my graph. Now the range on this old guy, this original parent function, the range, are basically y is greater than 1, y is less than negative 1, right? But we have a couple of vertical changes that have occurred, okay? So this minus 4 and this plus 2 will affect that. Those are vertical changes. So first thing we would do is dilate, multiplying the y's by 2. This would be y is greater than or equal to 2 now. This would be y is less than or equal to negative 2. Why? Because we have vertically stretched the graph. And we've downshifted. So we're going to take away 4. Subtract 4. So y is less than negative 2. Y is greater y is greater than or equal to negative 2. Y is less than or equal to negative 6. This is our new range. I just applied the 2 green numbers in the order of dirt to my rule for range. I doubled and took away 4. And this gives me my new range, which I will write as, the range is negative infinity to negative 6 and negative 2 to infinity. So you had a lot of trouble getting it into that form. Right here. But that's okay. I would have accepted it this way too, right? There's nothing wrong with it. It's just a little different. Okay. This next part is sort of a memorization thing, or you can think about the graphs. Sine is an odd function. Cosine is an even function. Secant is an even function. Cotangent is an odd function. Cosecant is an odd function. Notice that only cosine and secant are even, because they're the only graphs out of all this garbage that are symmetric to the y-axis. It's just these two. All the others are rotationally symmetric, or you could say origin symmetric. Okay, so you could just memorize that if you want. It also means we could pull negatives out of sines, tans, and that sort of thing, but not pull a negative out of a cosecant. I mean a cosine. All right, and then the bonus problem is so easy. It is so easy. Write the difference quotient. If difference quotient is defined as f of x plus h minus f of x over h, then the difference quotient for sine is literally sine of x plus h minus sine of x over h. Bonus point. Okay? So now if you want to try finding average rate of change from r to r plus h, that's a little bit harder. Okay, and Amar, you did a great job with this problem. See? He already knows that, I told him. So, average rate of change from r to r plus h of the area of a sector with respect to r. Wow, this is complicated. But what's the area of a sector formula? It's the very first problem on the test. What's the area of a sector? You scroll all the way back to number 1. What was it? 1/2 r squared theta. Right. So this is sort of like your f of x. See? That's like your f of x. Average rate of change is f of x plus it's technically f of x2 minus f of x1 all over x2 minus x1. Things are a little different. We're not using x's, we're using radii. Okay? All right, so the function's not f, it's area, but we're going to use the exact same idea. So the area function at r plus h would look like this, 1/2 r plus h squared theta. That is the area function with r plus h inserted. That is 1/2 r squared theta with r plus h in it. Minus 1/2 r squared theta, that's just your f of x1. All over r plus h minus h, because those are the two x's they gave you. This is your x1, this is your x2. See? Okay, and all of this simplifies nicely into 1/2 r squared theta plus 1/2 h squared theta plus 1/2 times 2r h theta minus 1/2 r squared theta. So I just did a FOIL. The bottom is just simply, sorry, this should have been an r. Right there. The bottom is just simply h. So I did a FOIL. I did r squared plus 2rh plus h squared, and I multiplied by 1/2 theta. And you'll notice that this cancels out. Remember I told you anything that has no h would cancel out? There it is. You can even pop an h out on the top, so I'm going to have to come over here. Pop an h out, and you have 1/2 h theta plus r theta. Even the h cancels out. So the final answer to this problem is, I'll write it up here, the a rock from r to r plus h is 1/2 h theta plus r theta. That's the answer. And I think there's I think it's like that actually. The 1/2 gets pulled out. Oh no, there's a 2. Never mind. It's just the 1/2 is only on the h theta. Okay? Yeah. All right, so that's the test. That was a hard one. And then they asked us what would happen if h gets closer to 0. So what would happen to 1/2 h theta plus r theta if h went close to 0? What would happen to 1/2 h theta? If h got really small, what would happen? If h was 0.01, 0.001, 0.000000000001, this term would vanish, leaving you with something very interesting. Evidently, the average rate of change for very small changes of the area of a circle is its arc length. Okay, so let me just show you what this means real quick, since we're done. Imagine a circle. Imagine an arc on a circle. Let's say this little piece. Imagine the sector. Okay? And imagine growing the radius just a hair. So now it's r plus a hair. The circle, of course, would grow just a hair. And, of course, the arc length would grow just a hair. Right? If you find average rate of change between here and here for the areas, the amount of area that it grows by is just this little segment here. So if you shrink this down, this picture, down to this, where these are really close, what amount of area just got added in there? One arc length of area. Tiny little arc length of area filled that gap, extending the circle just infinitely small amount. All right, we'll talk more about that next year. That's instantaneous rate of change. And I'll post all the videos, so except maybe chapter 4. Study hard.